Hello everyone, my name is Adeola Banis and I'm a fifth-year PhD candidate at Carnegie Mellon University. I'd like to invite you to learn more about our paper titled Bleep, Motor-Enabled Audio Side Channel for Constrained UAVs. This is a collaboration between myself, Dr. Hae-Young No of Stanford University, and Dr. Pei Zhang from Carnegie Mellon University. In our paper, we focus on small UAVs that are performing sensing tasks indoors, in environments that may be difficult or dangerous for people to be in, for example, doing inventory checks on very high warehouse shelves, or investigating fast-moving machinery while in use. In these environments, the metal nearby can sometimes momentarily disrupt the radio frequency links between UAVs. When this happens, it appears as if a UAV has been lost, which might trigger reorganization, when in fact it's having a momentary communication lapse. So what could the UAVs do in order to indicate that they are still present when their main communication channel is gone? We examined multiple modalities and chose sound as the best one for cluttered indoor environments. Now you may ask, how can UAVs use sound as communication since they produce so much sound themselves simply by flying? To answer that, we look at the sound that's produced by the motors and propellers during flight and figure out a way to use that as a sound source to partially counteract the high intensity of this noise. So how does this work? We detail the main steps needed to use motors as a signaling source for small UAVs. Firstly, we identify what about the motors can be changed during flight without losing controllability of the UAVs. We determined that with the small pulse width modulation driven motors in these UAVs, we can change the PWM frequency and without changing the power delivered to the motors. Secondly, we need to select a frequency modulated signal that is easy to detect in the high amplitude of noise. From our characterization of the frequency properties of the sound produced by UAVs, we selected a linear chirp as a simple, distinctive signal that is easy for the motors to produce and also easy to detect in the high amplitude of noise. Thirdly, we must ensure that these small UAVs are able to detect and decode the signals, even with the limited memory. In the paper, we detail a low memory chirp multiplication implementation that is able to detect and decode signals from multiple UAVs at distances up to 4 meters. Now you might be asking, but does it fly? And the answer is yes, it does fly. If you'd like to see it in action, please come to my full talk or have a look at the paper in which we have a link to the video of it in flight. Thank you for your interest in our paper. I invite you again to view the full talk, and if you have any questions, I'll be happy to answer them. Thank you.